Right. So, so the topic of this talk is the Zilber-Pink conjecture. So this, is a kind of conjecture which unifies and very much extends Andre Oort and Mordell Lang, but it's very much open conjecture, and it sort of arose independently in three different versions. So there was the work of Zilber coming from model theory, the work of Bombieri, Massazania, who were studying some problems, coming out of a question of Schinzel, and Pink in the most general setting. So,
by the way, when you say Mordell Lang, what do you mean? What's Mordell Lang?
Well, I'm going to say that in a minute. So, yeah. So, okay. So the talk will have three parts, and the first part is essentially, going from Mordell Lang to Zilber-Pink. And the second part is somehow the statement of the Zilber-Pink conjecture and some examples that illustrate its different faces. And then in the third part, I want to talk about the point counting strategy. So, I mean, this is sort of a very grand unified conjecture, and a lot of methods have been applied to solving it. Of course, you have the whole Mordell Lang, via Diophantine approximation, all the different approaches there. And for Andre Oort, you also have equidistribution approaches. And so there are very many approaches to the different parts of this problem. And but then I want to just describe how the point counting can be used to approach some of it. All right. So I want to start very briefly with the Mordell Lang picture, although I won't go into it in much detail because I want to switch pretty quickly to the multiplicative setting. So this would just be sort of fairly sketchy. So somehow the conjecture here is Mordell conjecture. Of 1922, and that's proved by Faltings in 1983, that if you have a curve of genus 2 or more, then it only has finitely many rational points. So, curve. Now, in the same paper, of course, Mordell proved the finite that the group of rational points on an elliptic curve is finitely generated group, and then that was generalized by Weyl to a billion varieties. And now you had this strategy to try and prove Mordell's conjecture by embedding V inside its Jacobian and intersecting, so let's call it J, and then intersecting, let's call this map phi. So you've got some curve, and you've got this curve inside the Jacobian, and you intersect it. The Jacobian is a group, and you intersect it with the rational points, which is finitely generated. So you're intersecting curve with finitely generated group. Now then, this Jacobian, of course, is an abelian variety, and so it arises as if it's G-dimensional, then it's C to the G modulo a lattice. And then the Manin-Mumford conjecture said that if you embed V in its Jacobian, and instead of looking at the rational points, you look at the torsion points, which are, in some sense, they're like the points which are rational up here with respect to the lattice. And the conjecture there was that this was also finite intersection unless your curve, the embedded curve, happened to be an elliptic curve. So in particular, if it was genus 2 or more and you embed it in its Jacobian, then the exceptional case can't occur and you get finiteness. So that was Mann and Mumford. And then Lang really started playing with these statements and I guess tried to put these two things together by saying that you have a subvariety, so Mordell Lang.
Okay. Yeah, I see.
You have a subvariety V of an abelian variety, and you have a finitely generated group, finitely generated. And then, well, in order to recover Mann and Mumford, you want to be able to take roots. So you intersect V with the division group of this gamma naught. So you look at anything that multiplies into this finitely generated group so that this so you intersect your subvariety with the division group of a finitely generated group, and the statement is that this is contained in finitely many cosets of abelian subvarieties by elements. So let's call these cosets T of abelian subvarieties by elements of that group, the division group, which are actually contained in V. So this V, maybe I should draw a picture. We'll come over here. So your variety V contains finitely many of these T, which are cosets. Maybe they're individual points, and that accounts for all of the points of V in this division group. So in particular, if gamma naught is a trivial group, then the division points are the torsion points, and you recover Mann and Mumford. And in general, it's finitely generated. If you forget about the division points, then you recover this Mordell in this more general form. Right. So then, okay, this version was.
Mordell conjectured. I think he conjectured that in thinking of this is why it's true. By that
Mordell.
Yeah. I don't think he thought about the division group. I mean, to him, the dichotomy between higher genus and genus 1 was exactly this.
Right.
Picture. Maybe Land says it's.
But.
And Weyl also, of course, who was trying to prove.
Yeah, well, I think people try to prove it this way. Absolutely. So anyhow, so this finally was proved after Faltings proved the Mordell conjecture, then there was Voigt's proof, and then Faltings. So this, well.
Raynaud proved it.
Raynaud proved the Mann and Mumford conjecture. I should have said that. Raynaud in about 1983 or 4 proved Mann and Mumford. Anyhow, then finally this full statement got proved by Faltings, Raynaud, Voigt, Faltings. Sometimes there are, anyhow, and there's a semi-abelian version and so on. But anyhow, that's just a sort of a sketch of those statements. But somehow now I want to move to the multiplicative case, because Lang also began playing with the multiplicative versions of these statements, some of which had already arisen, like the unit equation. Some of these things had already arisen in work of Siegel and Mahler and other people. So in the simplest case, you look at a plane curve, if you like, V contained in multiplicative group squared, defined by fxy equals 0. And so you're solving f of xy in the first case in roots of unity. those are the torsion points. So that's the analog of Mann and Mumford. And then the statement is that you get only finitely many unless V is of a specific form, that is essentially a subgroup up to a translation by a torsion point. So in other words, unless F looks like this, all right, where n and m are integers, not both 0 and zeta is a root of unity. Let me not write all of that down. On the other hand, if you try and solve fxy equals 0, so you can think of x plus, well, you can think of x plus y equals 1. That's the unit equation, but it's not so interesting in roots of unity. But in the next case, if you try and solve it for x and y in a finitely generated subgroup, let's say generated by C1 up to Cn, okay. Then this is essentially, well, this is the Mordell-Lang without the division. This is just solving the equation in a finitely generated group. And then, okay, you get finitely many unless, well, it's always the same statement, except now this, unless you're essentially a coset of a subgroup, but now the coset can be, so let's call this subgroup gamma naught. And then if you solve it in the division group, of gamma naught, then it's finite unless you're a coset of someone in the division group. And if you go to higher dimensions, then you're taking a subvariety of C cross to the n, and you try and find points on your variety in either of these categories, and the answer is that the points in question are in finitely many cosets which are contained in V. And the cosets are cosets of torsion points in this case, or cosets of that group, or cosets of the division group. So this now is the multiplicative analog of, well, of Mann and Mumford and Mordell-Lang with or without division, as you prefer. All right. So, and I should say that in this statement finally was proved by Laurent in about 1983 or 4. That fool. And okay, and the statement for curves, I should say these were theorems of Liardet in the finitely generated case. So then so now we have André-Oort conjecture, which was somehow formulated by, in slightly different versions by André and Oort, but in both cases by analogy with Mann and Mumford. So there the analogy is that you're now solving f of xy. In the simplest case, if we're thinking of V in C squared considered as a product of modular curves, we're taking a curve, fxy equals 0, and we're trying to solve it in singular moduli. So these are the analogs of the torsion points, the special points. So this is André's theorem from, I think, 1998. Well, you have the various analogies, but in the general case, you've got a subvariety V of a Shimura variety X, which could be C to the n, but in general, it's general Shimura variety. And you have the analogous statement that the special points in V lie in finitely many special subvarieties T contained in V. And these special subvarieties are things associated with the geometric structure of the Shimura variety. So these two statements look very similar, and it's a natural thing to try and put them together, and that is somehow one source of this conjecture. So this is the way, this is Pink's source, and I just want to explain the picture, which looks like this. So your Shimura variety looks like this. This is a Shimura variety, and it might typically be AG, parameterizing abelian varieties. And then over each point here, of course, is the corresponding abelian variety. Over X, you have AX.
So before you go to that, we know it for AG, but we don't know the above board for Andre Ort is not known.
Right. So Andre Ort is open in general. Right. So this is known for AG, and that's in the work of Jacob Zimmermann. So I didn't get fully time in the first lecture to explain that slide, and I'll say a little bit more about it later. But somehow the last missing ingredient is an arithmetic ingredient, which Jacob supplied in the case of AG. But in the more exotic Shimura varieties, it's still open on account of that arithmetic element that I'll talk a bit more about a bit further on. But for the moment, I just want to talk about conjectures and the sort of the conjectural picture. So now you can form the universal family of abelian varieties. That's a natural place where all of these people live. So let's call that XG, the universal family of abelian varieties. So in this space, of course, we've got all the abelian varieties, and we've got the Shimura variety itself, if you like, appearing maybe as the zero section or something like that. And these things also have a structure of special subvarieties and special points. And what are the special points? Well, down here, you've got the special points on the Shimura variety. Those are the CM points, the abelian varieties with the maximal amount of complex multiplication. And on the fibers, the abelian varieties have torsion points. And the special points of the universal family, however, are the torsion points on the CM abelian varieties. So now you can formulate the Andre Ort conjecture here. You can just say it, that if you take a subvariety here, that the special points lie on finitely many special subvarieties. That was formulated by Andre, and he even, so the simplest case of this, I should say, is the Legendre family. So here you just take the lambda line, missing 0, 1, and infinity, and here you put the elliptic curve E lambda, given by y squared equals x minus 1, x minus lambda. So this is a moduli for elliptic curves with their 2 torsion. So this surface defined by this equation is the simplest example of that. And in this case, in fact, Andre proved his mixed Andre Ort, that if you take a subvariety of this total space and go looking for torsion points on CM fibers, that it's finite unless it's a torsion section. But the problem over here is that, so now if you take a CM abelian variety, its torsion points are really special. So if you take a subvariety here, you recover Mann-Mumford. But if you take an abelian variety which is not CM, then its torsion points are not special. And this is a very strange situation, that your generalized conjecture sort of implies small pieces of Mann-Mumford, but not all of it. And this is where Pink's idea, or what he realized, was that if you have a torsion point here, it's not special, but it lies on a torsion section. And the torsion section, which is special, and here you have a subvariety, whose dimension, if it's proper, subvariety is less than the dimension of the fiber, so that this dimension plus this dimension is less than the dimension of the total space, and you have an unlikely intersection. You have an intersection that somehow is dimensionally unexpected. And this was somehow how he came to this idea of unlikely intersections. I'm going to give this, so this is just motivation. I'm going to give the statement in a minute. But now I'd like to, I guess, talk a little bit about the way Bombieri-Massezania, well, not their motivation in this problem of Schinzel, but somehow the kind of question it generated. Because this now is a conjecture in a mixed Shimura variety, but actually this conjecture gives you new things even in C cross to the n, and even open things there. So this is the Bombieri-Massa, in a series of papers, they started proving cases of these things. So one way to make this multiplicative Mordell-Lang look a bit more like the Manin-Mumford is to do the following thing. So you have fxy equals 0. We're in C cross squared. And we've got this group C1 up to Ck. So what I do now is I form a new curve. So this is the curve V. I'm going to form a new curve V star in C cross to the K plus 2. And what is it? V star is the set of points that look like xy with fxy equals 0. And then C1 up to Ck, those constants. So this is a curve in the space. And now I look for points on this V star. So look for points satisfying two independent multiplicative relations. I can assume the C1 up to Ck are multiplicatively independent, because that won't change the division group. So if you look for points satisfying two multiplicative relations, what you end up with is two relations that involve x and y. And if they're independent, those two relations will force x and y to be in the division group of C1 up to Ck. That's what they do. And that means that you recover, if you like, Mordell-Lang. And also the two independent relations give you a coset of codimension 2. V is dimension 1, so it's an unlikely intersection. So in this way, we also, if you like, by unlikely intersections, we recover Mordell-Lang, at least in the multiplicative case, but that works in the other case as well. But now all of a sudden you have a whole bunch of new problems, because you can now look at a curve which does not have constant coordinates. Maybe it's a curve, so this is the kind of example they give. You look at so t will be a parameter, so t is in C, say, and we look at the curve, say, t, 1 minus t, 1 plus t, 2t squared, C1, C2, C3. And we look at points on this curve satisfying two independent multiplicative relations. Now, those two relations might both be on t and 1 minus t, and then you're solving the multiplicative Manin-Mumford. They're going to be roots of unity on that curve. Or they might relate two of these guys to this, and then you're solving Mordell-Lang. Or they might just be two independent relations on those things. And then it's a whole other new problem, which goes far beyond Mordell-Lang. And so, right, so this is the case. In fact, I mean, I'll get to it later. But the case of curves, let me just say it now. Curves V in C cross to the n, that's a case where this conjecture, that's a case where this conjecture I haven't stated yet is known. That's due to Morin. And if you, for surfaces in C cross to the n, it's an open conjecture. The conjecture I haven't quite formulated. All right, so now actually I should just come over here and formulate the conjecture. How am I doing? So here it is. So we have a mixed Shimura variety X, which, well,
I understand that Pink would formulate this.
this is Pink, yeah. So Zilber formulated it.
Did it for sure, right?
No, Zilber formulated it in the semi-abelian. He formulated it in semi-abelian case. Pink made this general formulation, but it's already open in even if there's no, I mean, even in the multiplicative group. So you have a mixed, but I mean, this is just a formulation, all right? So this is some variety X, and it has a collection which I'm going to call curly S of special subvarieties. So in the multiplicative case, these are torsion cosets, and if it's a Shimura variety, then they're the special subvarieties, which I've explained in the modular case, exactly what they look like. All right, and now we have a subvariety, and now we have a definition. So a subvariety of V is called atypical if A is a component of V intersects T for some T which is a special subvariety, and A is atypical in dimension. So that's a definition. And now we have the conjecture. Oh, right. So no, I know we need another line. Oh no, okay, we can just state it like this. So for a mixed Shimura variety X, and V is a subvariety of X, all right, so I should have put in another line. So now we can form the atypical set by simply taking the union of all of those, of all atypical subvarieties. And the conjecture is that then the atypical set, so I call that a set because on its face it may not be a subvariety, it's a possibly countable union. That's the point. This set is always countable, so there are somehow countably many possibilities for this thing to happen. And then the conjecture is that actually then the atypical set is a finite union of atypical subvarieties. Now, you have to be a little bit careful here because it doesn't say that there are only finitely many atypical intersections. It says if there are infinitely many, then there's a bigger one that contains all of them. So you could say there are finitely many maximal atypical. Yeah, so you have to say things like that. Right. And if the dimension of V is one less than the dimension of X, then the only way to be atypical is for right, because then the expected dimension of a component is T minus 1. So to be atypical, you have to be contained. So if V is just one dimension less than X, then this conjecture reduces to Andre Oort for a Shimura variety, or Mann and Mumford for a CM abelian variety, or things like that. All right, so that's the conjecture. Right. Now also, okay, so there are different ways of formulating this, and there are sort of different words. So Pink's conjecture actually only talked about unlikely intersections, which was where the dimension and where you expect this to be empty. And the different formulations are equivalent in some cases and not quite equivalent in other cases, maybe. And so there's a few words. You see the word unlikely, atypical, anomalous intersections. I don't know, I've sort of gone with Boris's word, the intersections which are atypical in dimension. Anyhow, it's the same idea. Right. Now, I want to talk about what this conjecture says for curves. So consider a curve V contained in X. Curves are good because they don't have many subvarieties. So the only possible subvarieties are V itself and points. So the curve V itself is atypical if it's contained in a proper special subvariety of X. And if it isn't, then the atypical intersections are all points, and then it's truly a finiteness statement. There should only be finitely many points like that. And that brings me now to the theorem of Morin, which is up there, Morin. And I forget the year. So let V in C cross to the N, a curve not contained in any proper special subvariety, then, well, V has only finitely many atypical points. So here, okay, and Morin proved this when V is over Q bar. Bombieri-Mastrezania had proved when V not contained in any proper weakly special, and then later it was also, they extended it to V over C. But right. And this conjecture is open in general for surfaces. I think Bombieri-Mastrezania have some results for planes. Right, so what else did I want to talk about? I wanted to talk about, I wanted to talk about just a couple of other examples of what this conjecture says. So I want to talk about the Mastrezania work on anomalous torsion points. So you can consider over lambda, you can consider the family of E lambda cross E lambda. Take 2 copies. And then in the case they chose somehow a point on the generic fiber. You take a point, say P lambda, to simply be the point with coordinate 2. So that's now square root of 2 minus lambda. I mean, this is the case, and this is 6 times 3 minus lambda. So this gives you, if you like, some kind of a section, P, right? P lambda, Q lambda is now a point on E lambda for each lambda. And these points are generically are not torsion, which you have to check. But then what the Zilber-Pink conjecture says, so now you look at for which lambda can it be true that both P lambda and Q lambda are torsion points. And that represents the torsion sections, if you like, have codimension 2. It's 2 conditions. And P lambda is torsion, Q lambda is torsion. And so the conjecture says that there are only finitely many. And Masser and Zania proved this initially in this example and then in much more elaborate examples. And I want to talk about some extensions of this also by Barroero and Capuano, who said you can take E lambda to the N and you take a curve by choosing, if you like, a sort of generic point which has no linear dependencies. So you get a curve now in E lambda to the N over this lambda line, and you look for points where the points, so let me call them now just P1, P2, up to Pn, but they depend on lambda. And you ask, for which lambda can it be true that all these points in this, in e lambda to the n, satisfy two independent linear conditions in that abelian variety? And anyhow, and so Zilber-Pink predicts, and they prove that you only get finitely many, unless you're in the exceptional case that this is satisfies identically one linear relation. But I want to somehow make the point here that Zilber-Pink also implies other things in this case, because there are other kinds of special relations. So you could also ask for lambda to be special, to be a CM point, and to have one relation on those points. And Baruero also proved that. So but I mainly wanted to mention that somehow, particularly in the mixed cases, you get quite interesting sort of, well, peculiar mixed problems. Right. Now, I want to talk now about, so that was basically my part 2, and now I want to talk about the point counting strategy, which I want to talk about with reference to some joint work with Philip Habeger. And this is with respect to a curve V inside a product of modular curves, say C3. Cn in general, but C3. So Zilber-Pink predicts if V is not contained, I mean exactly as over there, if V itself is not atypical, which means not contained in a proper special subvariety, then there should only be finitely many atypical points. Now, what do the atypical points look like? You have to look at what the specials could be.
You didn't say in these, maybe the Bombieri case, is Atypical theory used because in some of these cases, because of, well, now you've got Mordell as part of some of these things. So like in this Massa.
Well, in this uses Voiter type things. I was going to mention it a bit later, but the Bombieri-Massazenia work, I mean, a very strong ingredient there was the bounded height of the so-called likely intersection. So that was somehow the key arithmetic input. And then you have...
See, I call these horizontal and yours vertical. So in the horizontal theorems, which are like Mordell conjecture, there is no proof without Atypical theory.
Right.
So it'd be good to know. So since now you're getting to point counting,
yes,
which doesn't have.
This is going to be a point counting approach. I was going to make the point, well, let me get to it. So there should I want to right. So I wanted to first make the point that these atypical points, they can look in a couple of different ways, because the special subvarieties here are cut out by modular relations and setting coordinates to be special. So a typical atypical point might be x, y, z in V, such that there's a modular relation between x and y, and there's a modular relation between y and z. That's one way to be atypical, right? This defines a special curve. This is a curve. And if they meet, that's atypical. But another way you can be atypical is if x is a special point and y and z are related like this. Or, of course, if x and y are just special. But then you're talking about the Andreault conjecture on the projection. All right? So there's a number of ways to be atypical, and I'm only going to talk about this way, just to illustrate how it goes. And now I should say what we prove. So theorem, and this is Philip Haberger. This is true if V is what we called asymmetric. And asymmetric means that if you look at the non-constant coordinates on this curve and their degrees, that the degrees are all different, with one possible exception. We can allow anyhow. So that's what asymmetric means. It's not a nice condition. But the point I want to make is that, right, so so now let me maybe come over here. Because here I wanted to say something. Well, so the point counting strategy, so where do I have this? Right. So in the point counting strategy, things tend to sort of devolve into two issues. And the one of them is Axe-Shanwell. And then there's some kind of arithmetic issue, which in this case is a large Galois orbit. Okay? And in the Andre-Oort case, these correspond to somehow the Axe-Lindemann, which characterizes the sort of maximal algebraic subsets in the pre-image on the one hand, and here, of course, the Galois orbits of special points. And this is what Jacob managed to do in AG. And this is somehow the remaining ingredient that's missing. And I wanted to make 2 points about this. One is, so this asymmetry condition for us is going to imply the arithmetic condition we need, which I'm going to write down. And that's all somehow that's what we use it for and need it for. And the other point I wanted to make, because I feel I should have made this point last time, is that so when you do a point counting approach to Andre-Oort and you generate, via counting, you generate algebraic subsets in the pre-image, and then the Axe-Lindemann says the maximal ones are weakly special, I wanted to make the point that this Axe-Lindemann and Axe-Shanwell only ever talk about weakly special things. The arithmetic, there's no arithmetic here. These are just about varieties over C. But that somehow once you've discovered that you've got a weakly special subvariety that contains special points, that makes it special. Just like if you're a coset that contains a torsion point, you're a torsion coset. And that somehow works here too. So somehow, even though the functional transcendence moves into a sort of a weaker notion, then you remember which points you were actually looking at, and then right. So now I want to describe this strategy. And all right. Right. So what the asymmetry, let me just put it here. Asymmetry ensures that we get the arithmetic condition that we want, which I'll write up in a minute. So here is, we've got the J function mapping h cubed down to c cubed. We've got a subvariety here, and we've got x, y, z in V atypical of this form. There's modular relations between all the coordinates. And the asymmetry condition ensures basically that x, y, z, that this extension degree is greater than or equal to some positive constant depending on v, maximum of n and m to some positive power. That's what we need, and that's what the asymmetry gives us. And maybe I can just mention that so this is for v defined over q bar, but in fact, it's possible to prove this same theorem of v is not defined over q bar. And then you simply put here a field of definition for your variety, and then this bound follows by gonality estimates on the modular curve. So that, I mean, anyhow, just to give it some extra plausibility. But, so what do you do? Up here we have our fundamental domain cubed.
The gonality estimate is the power of n, right?
Power of n. Any power, any positive power of n. So up here, of course, in the fundamental domain, you can find pre-image of this point. And what you can prove then is that if these are related like this, of course, v is GU for some G in GL2Q, and HV equals W for some H in GL2Q. And what you can prove is that the height of G and H, and this is very elementary, is at most C times the maximum of N and M to the 10th power. You know how to write down representatives of the matrices, and then you see how far away they take you, and then you reduce. This is a very elementary thing. So what this means now is that if you have an atypical point on V, then it has a lot of conjugates. And each one of these conjugates gives you a pair like this G. It gives you a triple here and a pair here. And now this will be our rational point. But I have to tell you what set it sits on. So now I do this. I make a definable family. So here is Y, which is the set of U, V, W, G, H in H cubed times GL2 plus R squared, such that GU equals V and GV equals W. This is simply a semi-algebraic family. There's nothing happening there. And on the other, so that's a definable family. And then I have Z, which is the...
One of them is H.
Yes. Yes. Thank you. Sorry. Now I have J, the pre-image of V intersect the fundamental domain, and that's definable set. And now I take X to be the set of GH in GL2R squared plus, it doesn't matter, such that YGH intersect Z is non-empty. That's a definable set. And if you get an atypical point here which has large n and m, or n or m, if either n or m is large, then you're going to get a lot of rational points on this set. And we're going to apply counting to this set. And I want to notice two things. Firstly, that Y, the fiber of this family, intersected with Z. Now, according to our according to our assumptions, these intersections are always finite. It builds in the X-Shanwell a bit, but because of that, it's uniformly finite by O minimality. That's that. Now, the other thing I want, so we're going to count points here, and of course, the statement is simply going to be that if you get a point, an atypical point of large max nm, then you're going to get an algebraic curve here. And, all right. So, and then the punchline is going to be, so you get a family of these y's, you get an algebraic family of y's that all intersect your curve z. Well, okay, let me say the other thing first. So this set has a bit of a problem from our point of view, because you see, if you have a point here like this, then you can change either G or H by a stabilizer of U, and you won't change, right, anything. And so this set here is totally fibered by stabilizers of the relevant points. And so X alg equals X. The algebraic part is the whole set. However, it doesn't matter because you see, if we have this X, Y, Z, it's going to give us all these conjugates. And so if the algebraic things we find stay in the algebraic parts, they never account for more than one point. So you need a slight refinement of the counting theorem, which says that the rational points on the definable set lie on a small number of algebraic pieces. And then that proves that one of those pieces can't lie in the stabilizer, and that the relevant intersection must move on the curve. And O minimality makes it quite direct to prove that these functions, if you like, the function that connects this point here to the relevant intersections, which are definable functions, will be differentiable outside of a finite set, and so on. So it's very easy to prove that they must move. And from the family of x's, then a one parameter family of x's, you complexify the parameter, and now you'll discover that this pre-image, which is a curve, is now contained in this family of curves. In other words, it's contained in an algebraic surface. And now Ax Shanwell has something to say about that, because it says that if you take the pre-image of V and you intersect it with W in H3, C3, and you take a component, then the dimension of that component should be the dimension of, well, W plus V minus N. But here the component will actually be all of V. And so that's going to tell you now, Ax Shanwell tells you that this pre-image is contained in something weakly special. Now, weakly special, proper weakly special, it could mean that some coordinate is constant. But if the coordinate is constant, then all of these things lie in one Hecker orbit of that constant. And then this theorem is very easy to prove, because in Hecker orbits, you always get large Galois orbits, and the same proof works much easier. So that is how it goes. And I should say here that, of course, for this case, when you're only looking at when is the pre-image of V contained in an algebraic W, it's really not the general case of Ax Shanwell. It's what you might call Ax logarithms. It's the algebraic independence of the logarithms. And this follows, and this was proved in general by Ulmo and Yaffe, but they're using monodromy and the theorem of Deline and Andre about the Zariski closure of monodromy. So in this case, you only use Ax logarithms. But I wanted to...
You say what asymmetry is?
Yeah, asymmetry.
It implies.
Yes. The condition is that of the non-constant coordinates on V, the degrees are all different with possibly one repetition. So this V, yeah, that's the condition. So of course, generically you don't have that, so this excludes the generic case. And yeah, so I wanted, I guess, so this approach can be carried out more generally. So Philip and I, for a start, proved that you can actually, well, so let's call it conditional ZP for C to the N. So you can more or less carry out this same proof for a full proof of Zilber-Pink. Now here we were only talking about points, and it's then you've got something whose Galois orbit you can talk about. When it's some higher dimensional atypical set, what we show first is that you can always reduce sort of a higher dimensional atypical set on one variety corresponds to an atypical point on some other variety. So you can always get by, or in other words, you prove Zilber-Pink if you can prove that on every variety there are only finitely many what we call optimal points. And maybe, so anyhow, maybe I won't go into it, but they're points which are atypical. and which are not contained in any larger atypical set which isn't more atypical. It's just optimal. I mean, and it's too late to start giving definitions in the last 2 minutes of a talk. But you see, with this general conjecture, right, the other way of saying it is that there are only finitely many maximal atypical sets. But some sets can be more atypical than others. And the measure of it, how atypical, is given by A. If you take your subvariety A, you take the smallest special containing A, and you look at this difference in dimensions, and that's called the defect. And that somehow, the smaller that is, the more atypical you are. So the optimal point is a point on your variety. Well, an optimal subvariety is one that you can't increase with the same defect. It's just reformulating the same conjecture, but we end up with a, if you like, proving that it's enough to prove this about certain kinds of points for which we can then make a conjecture about their Galois orbits, and then you can carry this out in general, and that, right. So again, that is sort of leaving behind, I mean, I've been trying to talk about the point counting, so I'm kind of not talking too much about the arithmetic. But here this also leads back to heights. In the GM and the abelian variety case, you have this bounded height conjecture for curves of Bombieri-Massezania and then Habegger in general. And then this also can be rephrased. Here, the heights of the special points can be used then to prove the Galois orbits via Masse-Wurz-Holz. And here, this can also be framed as a conjecture about heights. So somehow, but right. So we were able to prove a full Zilber-Pink conditionally on the requisite arithmetic. And Chris Dorr and Jimbo Ren have carried that out to some extent in a general Shimura case, although there are some more conditions. Some of the things that that are very trivial in the modular case somehow become non-trivial in general. So you end up with some additional arithmetic issues. Yeah, but I think I'd like to stop there, and thank you very much again for the invitation and for the attention.